All right. Hello, everyone. I will be presenting my work about the metallicity structure of the Milky Way halo. And my name is Akshara Viswanathan, and I'm a first-year PhD student working with Else Stackenberg and her Pristine collaboration, and Amina Helmi and her team in Kapteyn. I would also like to thank Helma Koppelman and Chris Yukim for their useful suggestion throughout this work. And because I started my PhD in the era of remote working, I would also give credits to Zoom. So moving on, for the next 9.5 minutes, I will cover about why do we want to study the Milky Way halo and the importance of that, because we've had a lot of talks about the halo today. I will quickly skim through that. And a little bit about the Pristine survey, and how we select the halo stars in my sample and cross-match them with the Pristine photometric metallicities, and a little bit results about the hot thick disk contribution in my sample and the metallicity distribution across various distances and lines of sight, and some ongoing work regarding the substructures that we see in the metallicity space. Moving on, why do we want to study the Milky Way halo? There could be two main reasons. Because it talks more about the assembly history of the Milky Way in general. It talks about most of the past accretion events, etc. And we have more metal poor stars in the Milky Way halo. And why is it difficult to study the Milky Way halo is most of the stars are distant and scarce. And at those distances, the Gaia parallax is really poor. And we're looking at the halo from a vantage point in the disk. Now, in our method, we use the reduced proper motion selection method for selecting the halo main sequence stars. Why main sequence stars? Because they have simpler absolute magnitude color relations. So they can be used to reliably estimate the photometric distances. And we use the reduced proper motion parameter, which relates proper motion in photometry, to select the main sequence halo stars. This is the formula for reduced proper motion, and this is a reduced proper motion diagram, the RPM parameter versus the Gaia color. And here we apply a high tangential velocity cut to select the halo main sequence stars. And the advantages of using this selection is because this is a distance independent way of selecting the halo main sequence stars, and the main sequence stars are numerous in the halo, and we make use of the Gaia 5D sample, which is several times bigger than the Gaia 6D sample. And one of the major advantages is that we're able to estimate the photometric distances reliably. So within the reliable color cut range, the distance uncertainty is down to 7%. So originally the catalog was produced for Gaia DR2. So with DR2, we got 11 million stars, and when Gaia DR3 came out, we produced the catalog, and voila, we have 47 million stars. So more stars means more science to do with the sample. And let me cover a little bit about how we study the metal poor stars with the Pristine survey. Pristine survey is a narrowband CHK survey in the Northern Hemisphere, and it uses the CHK filter, which is very metallicity sensitive. And this is a comparison of the Pristine photometric metallicities with the spectroscopy ones. And we have a coverage of more than 6,800 degrees square in the sky. And we study the inner galaxy, dwarf galaxy. It's used to select the PHP stars. We study the disk, the bulge, and also the halo. So circling back to the RPM sample that I started with, I cross-matched the halo RPM halo stars with the existing spectroscopy surveys, and the cross-match numbers are listed here in the table. And then I cross-matched them with the Pristine photometric metallicities, and we have 700,000 stars, which is a huge cross-match. And these are the metallicities from the spectroscopy surveys. And one common thing that we see here is the hot thick disk contribution. I will come back to this in a while. Now, this is the metallicity distribution from the Pristine photometric metallicities within the reliable color cut range, where the distances are more reliable. We have approximately 400,000 stars here. And more number of stars means a better characterization of the heliometallicity distribution, and more metal poor stars means a better chance of finding older substructures. We have a metallicity peak at around -1.6, which is consistent with the literature results. So in this plot, we see the hot thick disk contribution here. So by hot thick disk, I mean the kicked up thick disk stars that are in halo orbits, but have similar chemical properties to the thick disk stars. Because we have reliable distances and photometric metallicities, I thought of quantifying the thick disk at different distances or different scale heights. The result is shown here. So there are several conclusions that we can make based on this plot. One being the peak of the thick disk is getting shifted to a more metal poor end, and it almost disappears at a higher scale height of like around -10 kiloparsec, and the dispersion increases as well. And the relative weight of the thick disk continuously reduces too. Now the peak of the entire halo distribution also moves to a metal poor end. And the metal poor tail that we see, the third component, it shifts to a very metal poor end, and the dispersion also reduces heavily. So, oops. Yeah, this is the sky region of the RPM sample cross match with the pristine photometric metallicities, and it's color coded by the galactocentric distances. So to understand the metallicity distribution at different directions in lines of sight, I divided the sky region into several subregions that are symmetric about the latitudes and longitudes, and tried to plot the metallicity distribution at each region and compare it to the background halo. As a result of this, in the latitude region, absolute latitude between 20 and 40, we have at increasing longitudes, this is the metallicity distribution. We can see that the peak of the metallicity distribution shifts to a little bit more metal poor end. In this plot, that means that the peak shifts to more metal poor end towards the anti-center. And I continued this for different longitudes and latitude regions, and we see very similar results for higher latitudes. And I also tried to plot the metallicity distribution in low latitudes and high latitude region as shown in the sky plot here. And this is the metallicity distribution that we get. In low latitude, though we don't have a lot of stars, we can see that it mostly follows the background halo distribution. But in high latitudes, especially in high longitude and latitude region, we see a prominent metal rich bump. At lower distances, we were still yet to figure out what causes the metal rich bump. At higher distances, it could be due to the Sagittarius debris. This is still an ongoing work. I also tried to plot the metallicity distribution in different quadrants. So as we see from the plot, we don't have a pristine coverage in quadrant 3, but we see something very interesting in quadrant 4, which is an enhanced metal poor tail in comparison to the background halo distribution. And when I tried to look at the sky space of this region, I was able to see an overdensity of very metal poor stars that causes a substructure sort of thing. And when I looked at the stream finder streams in that region, this is the plot for the stream finder streams in the region. Stream finder is an algorithm which assigns a probability that a star belongs to a particular stream based on several other parameters. And this is what I observe in my sample. So we think it could probably be an extension of the Phlegeton stream and few the stream that crosses the Phlegeton stream, as we can see in this region. This is also an ongoing work. Being a part of this cool team, we also collaborate on several other projects. There is a Pristine Stream Finder project that is running in the team where we assign, where we find the metallicity distribution for the pristine streams, for the stream finder streams. And this is an ongoing work as well. As a part of this work, we are mining one of the lowest metallicity substructures in this work. And with Pristine NV, we will have greater than 30,000 stars in which are less than extremely metal poor category. So this way we will be leaving no stones unturned. So to summarize, in the metal poor halo, we are able to characterize the metallicity distribution of the metal poor Milky Way halo in different directions and lines of sight. And when it comes to the metal rich halo, we're able to constrain the contributions of the kicked up thick disk stars at different scale heights, and we will be able to characterize the metal rich bump at higher latitudes as well. And we also see a few substructures in the sample. So the structures in and around Phlegethon could be studied more in detail with the sample, and we will also be able to probe a lot more substructures. So thank you for providing me this opportunity to present my work. You can reach me out at any of these places to follow my work, and I will stop for questions.
Thanks a lot for this great talk. Do we have questions already coming up? I'm sure there's tons of interested questions. Yeah, Tilman, you want to read out, or should I just read it?
I can also read it out. Hi, Akshara, really cool result, nice talk. I'm wondering about the tail of your MDF. So I think in one of the first plots, your MDF stops at -4, but your last bin at -4 still has hundreds of stars in it. And so I'm wondering, does it and how does it continue to even lower metallicities?
You mean this one?
Yes, right.
Yeah, could you repeat your question? I did not understand the last part of your question.
So in this last bin around -4, you have 100, 200, 300, 400 stars, right? But then there's the sudden drop to no stars below -4. Is this physical, or is just the pristine photometry not able to distinguish between -4 and below -4?
This is just the coverage based on the current pristine candidates that we have, and I think it's just because it's a log plot, it's just more prominent, but it's just a normal thing, I guess. If it's not a log plot, to have less number of stars in below the extremely metal poor category.
Okay.
Yeah, I guess it decreases by 100 folds normally.
Okay, thank you.
Is there any other question? I don't see, but I have one question. When you show the metallicity distributions for different latitudes, if you can go to that slide. Yeah. You were talking about, or in your conclusions, then you said something about this might trace the stars kicked up out of the metal poor thick disk. I wonder, I think I'm coming from from a simulation community, and I think it's still not really clear if the thick disk is actually heated or if it was formed in a thick way with high velocity dispersion. And so I'm wondering whether you are able with this metallicity distribution functions to put stronger constraints, whether heating is more important or the formation was already with a quite large scale height.
I just used the term heated up thick disk mainly because we select the stars with higher velocities. So because it's a kinematically selected sample, most of the candidates that we will have will probably be heated up thick disk stars.
Okay, so you do a pre-selection on velocity dispersion.
Yeah, so this is not, yeah.
Oh, I see. Okay, we have a comment on the chat that the MDF drops significantly at -4, because that was the previous question. If there is no other questions, I encourage you to use the Slack extensively for further questions which might come up.